Just last week, I noticed this site was making rounds across Twitter in the creative dev circles, and a few folks from our pro and community discords too dropped the link recently, which definitely caught my attention. So I decided to dig into it just to see what all the buzz was about. And honestly, it's clear why everyone is talking about it. I have to say, the experience is stunning. From the design to the interactions, everything feels really polished. If I'm not wrong, the site was built by Off-Brand Studio and they've done an incredible job here. I haven't actually checked what exact stack they used, but judging by the way the animations flow, it looks like it could be built in Webflow, maybe with some Three.js handling the simulation and some of these effects, and GSAP powering the rest of the animations. There are quite a few effects on the page worth studying, but the one that stood out to me the most was this hero section. It features this immersive mouse trail animation, almost like a fluid mask, where your cursor reveals a second portrait image underneath the top one, and layered behind that, you have got this subtle fake 3D parallax effect, plus some wavy organic lines in the background that all work together to make the composition feel alive. To be completely honest, I knew I wouldn't be able to recreate even 10% of what they built, as there is just a lot going on here, and it's all executed at such a high level. But I still wanted to give it a shot, just to understand how something like that might be built from scratch. So after spending over 10 hours experimenting, I was able to put together a small demo, just the fluid trail part from the landing section. When you move your cursor around the screen, it acts like a mask that reveals a second image beneath the top one in real time, kind of like a soft, painterly brush stroke effect powered by a custom shader. It's a very simplified take and not nearly as advanced as the original implementation, but I thought it could be a solid starting point to understand how this kind of fluid reveal can be achieved with Three.js and custom GLSL shaders. In this video, I'll walk you through the code and how it works. If you find my work helpful, please make sure you leave a like on the video and subscribe to the channel if you haven't already. And if you'd like to access the source code for this project, plus hundreds of other similar micro projects and a brand new website template every month, you can check out the pro membership via the link in the description. Alright, let's jump into the code. First, let's talk about the assets we'll need for this project. We are basically working with two images here, one that sits on top and another that we reveal underneath as a part of the cursor interaction. For the top image, I grabbed this portrait directly from a website called Lumi. This is the image that shows up by default, the one you see as soon as the page loads. Then I needed a second image to use as the reveal layer, something that would feel visually distinct from the top one. So I generated this alternate portrait using AI, featuring a sleek black helmet that covers the face. This is the image that gets revealed inside the cursor trail as you move your mouse around the screen. Once I had both images ready, I removed the original backgrounds and added these soft curvy lines in the back just to mimic the layered, organic look from the original site. You will notice the top portrait uses a slightly lighter background shade, while the helmet version underneath is a bit darker. The contrast helps make the reveal effect stand out more clearly, just as the original. Both of these images will go inside the public directory of our project and we'll import them later as textures inside our Three.js setup. Alright, with our assets in place, let's move on to the HTML structure. First, I'll create a nav element just to mimic the layout from the original site. Inside it, I'm adding two elements, one on the left for the logo and one on the right for the menu label. In the site name div, I'll drop a simple anchor tag. This acts as a placeholder logo. And on the opposite side, I'll use a paragraph element with the word menu just to represent the menu toggler. Next, I'm creating a section with a class hero. This is going to be the main full screen area of our landing view. Inside that, I am placing a canvas element. This is where we'll render our interactive Three.js scene, the part that handles the fluid simulation and the image blending effect. And finally, below the canvas, I'll add a footer div with the class hero footer. Inside it, I'm just adding two lines of placeholder text. This is purely to show that you can stack any kind of content over the canvas, text, UI elements, buttons, whatever your layout needs. Alright, now that this structure is in place, let's move on to the styling. First, I'll bring in two fonts from Google Fonts. We are using DM Mono as our primary typeface and Righteous for the logo, both of which fit really well with the minimal, futuristic vibe we are going for. Next, I'll reset the default browser spacing by removing all margin and padding and setting box sizing to border box. Now for the base styles, I'll apply TM Mono as the main font across the entire body. Then I'll style all anchor tags and paragraph elements so they share the same look. They are going to be uppercase, bold, and slightly condensed with a clean monospaced feel. I'll make sure they don't show any underlines and align them to behave more like block elements for easier layout control. Next, I'll take care of the navbar. I'll fix it to the top of the screen and make it span full width. We'll add some padding around the edges and use Flexbox to space out the logo and menu evenly, aligning them toward the top. Then, inside the site name section, I'll apply Righteous as the font and increase the size to give it more character. This helps the logo feel bold and stylized. For the menu label, I'll give it some padding, round off the corner slightly, and use a solid black background with white text just to make it pop and feel like a clickable button. Next, I'll move down to the hero section. This is set to cover the entire screen and will hide any overflow to make sure everything stays contained inside the viewport. Inside the hero, we have got the canvas. I'll position it absolutely to fill the entire space and place it behind the rest of the content using a lower Z index. Then finally, I'll style the footer section. Its position at the bottom of the hero stretches across the full width and uses some padding and flexbox to space out the content on either side. We'll align everything to the bottom edge so it feels nicely anchored and doesn't overlap the main interaction area. And that's all we need for the styling. With the layout now clean and responsive, we are ready to jump into the JavaScript and start firing up the interactive fluid mask effect. Before we jump into the scripting part, let me quickly show you the shaders we'll be using in this project. I have created a separate file called shaders.js, and inside that, I'm going to paste each shader one by one and explain what each one does and what part of the effect it's responsible for. Now, just to be clear, I'm no shader expert at all. If you have been following my work for a while, you already know that I usually use AI to help me write these. In this case, I used Claude to generate the GLSL code for me, and it honestly took quite a bit of time and trial to get something that actually works inside a Three.js setup and gives me the exact effect I was aiming for. So let me walk you through them step by step. First, we have got the vertex shader. This one is very basic. It just passes the UV coordinates through from the geometry to the fragment shader, which we'll then use to sample textures later on. We are not doing any fancy distortion or vertex displacement here, just a clean flat pass through. Next up is the fluid fragment shader. This is where the fluid simulation logic lives. The idea here is to create a kind of trail based on how the mouse moves across the screen. It takes in the previous frame's trail texture, decays it slightly to create that soft fade effect, and then adds new intensity where the cursor moves. It does this by calculating the direction of the mouse movement, then projecting each pixel to see how close it is to that path. If a pixel is close enough to the movement trail, it adds brightness to that area, kind of like painting a stroke with a brush. The result is a soft, glowing trail that fades over time, and that's what we'll later use as a dynamic mask to reveal the hidden image underneath. Finally, we have the display fragment shader. This one takes the fluid trail output and uses it as a blending mask between two images, the top texture and the bottom texture. So when you are not moving the mouse, all you see is the top image, but as soon as you start interacting, the fluid trail reveals portions of the bottom image underneath with a smooth gradient blend between the two. The shader also includes logic to scale and position both images properly on the screen, kind of like how background size cover works in CSS. So no matter the image resolution, everything stays nicely centered and fills the screen. Alright, with our shaders ready, now we can move into the JavaScript and start building out the actual Three.js scene. Before we dive into the JavaScript, just a quick heads up, to save a bit of time during editing, I won't be writing the code out line by line. Instead, I'll be pasting it in larger blocks and using that extra time to walk you through what each part is doing and why it matters. This particular setup is a bit trickier than usual. There are a lot of moving parts here between the shaders, the render targets, and the interaction logic. So along the way, I did use help from AI to get things working just right, especially for structuring the render pipeline and making sure everything connects smoothly in Three.js. Alright, with that out of the way, let's walk through it step by step. We'll start with the initial setup. First, I'm importing everything we'll need at the top. We are bringing in Three.js. That's the main 3D library we'll be using to create and render our scene, and then importing our three shader programs from the separate shaders.js file, the vertex shader, the fluid fragment shader, and the display fragment shader. Together, these will handle all the rendering logic from how the trails are drawn to how the two portraits blend together on the canvas. Next, I'm setting up an event listener for when the window loads. Once the page is ready, it calls a function named init where we'll set up everything: the renderer, the scene, the camera, the materials, and all the mouse interactions. That's where the core of our entire setup will live. So now, inside the init function, let's start putting it all together. First, I'm selecting the canvas element from the DOM. That's the same one we added in the HTML earlier, and it's where we'll be rendering everything visually. All the fluid trails and image blending will show up inside this canvas. Next, I'm creating a new WebGL renderer and passing in that canvas. I'm enabling anti-aliasing to smooth out the visuals and setting the precision to high just to make sure we don't lose any detail in the shader calculations later on. Then, I'm setting the renderer size to match the current window dimensions and adjusting the pixel ratio, but I'm also cropping it to a maximum value of 2. That's just a simple performance safeguard. So if someone is on a super high resolution screen, it doesn't overload the GPU with unnecessary pixels. After that, I'm creating a new scene which acts as the container for everything we'll be rendering. And for the camera, I'm using an orthographic camera instead of a perspective one. Since we are just rendering flat textures across the entire screen, we don't need any perspective distortion, and orthographic projection helps keep everything pixel perfect and consistent. Now let's set up the interaction state. I am creating two vectors to track the mouse, one for the current position and one for the previous position. We'll use these later to calculate the direction and speed of the cursor movement. Then I've added a few control flags, one to track whether the mouse is currently moving, one to store the time of the last movement, and another to check whether the cursor is inside the canvas. These will help us decide when to trigger the fluid trail animation and when to let it decay naturally. Next, I'm defining the simulation size. I've set this to 500 for now, which means the fluid simulation will be calculated in a 500 by 500 texture. That should give us a nice balance between detail and performance. Now comes an important part, the ping pong render targets. I'm creating two separate off-screen buffers using WebGL render targets. These will store the state of the fluid trail from one frame to the next, so we can feed the result of the previous frame back into the shader and build up the trail over time. Every frame will swap between these two targets, one for reading and one for writing. At the end, I'm setting a variable to keep track of which target is currently active, and will toggle this every time the animation updates. Now that we have set up the core structure, let's bring in the actual assets and wire up the rendering materials. First, I'm creating two placeholder textures. These are just temporary, one filled with blue, one with red, and we are using them as stand-ins for now while we load in the real portrait images later. Then I'm creating two vectors to store the actual size of each image. This will be useful in the shader when we calculate how to scale and position each image properly so it fills the screen without distortion. Next, I'm setting up the trails material. This is the shader that drives the fluid simulation. I'm passing in all the uniforms it needs, including the previous trail texture, the current and previous mouse positions, the simulation resolution, a decay factor to control the trail fade speed, and a boolean that checks whether the user is currently moving their mouse. All of these values get updated live as the user interacts, and they directly affect how the trail is drawn in the fluid shader. Then we move on to the display material. This is the shader that actually gets rendered on the screen. Here we pass in the result of the fluid simulation, the two portrait textures, top and bottom, and a few additional values like screen resolution, device pixel ratio, and the original texture sizes. This material is responsible for blending the two images based on the mask coming from the fluid shader, so as you move your mouse, it softly reveals the bottom image underneath the top one. Once the materials are set up, I am loading the actual images. We are loading a top image which will be visible by default and a bottom image which gets revealed inside the mouse trail. Once each image loads, we update the texture reference and the size vector so the shader has all the information it needs to display the images correctly. After that, I am creating a full screen plane geometry. This is just a flat rectangle that fills the entire screen, and we use it twice, once with the display material which we add to the main scene, and one with the trails material which goes into a separate simulation scene. These two planes work together, one to calculate the simulation off screen and one to actually display the result on the canvas. Then I'm clearing both ping pong render targets. This ensures that we start with a completely blank slate, no leftover data or trails from a previous frame. Now I'm setting up interaction listeners. We listen for the mouse movement, touch event, and window resize. This lets us update the mouse position in real time, respond to mobile input, and keep everything responsive across different screen sizes. And finally, we kick off the animation loop. This will continuously update the simulation and re-render the scene frame by frame, giving us that real-time, fluid cursor trail that blends the images as you move. Next, let's go over the two helper functions we are using in this setup. one for creating placeholder textures and another for loading our actual image files. First, we have the create placeholder texture function. Here, I'm creating a new canvas element directly inside JavaScript. I'm setting a fixed width and height for it. This gives us a small off-screen surface that we can draw color onto. Then I grab the 2D rendering context from that canvas. That's basically what lets us draw shapes and colors onto it. After that, I set the fill style to whatever color we pass into that function and fill the entire canvas with that color. Once that's done, I convert the canvas into a texture using canvas texture. This texture behaves just like an image texture in Three.js, so we can use it anywhere in our scene, whether it's for testing, debugging, or serving as a placeholder while the real image loads. I am also setting its main filter to linear just to keep it smooth and prevent blocky artifacts when it's scaled. Finally, I return that texture so it can be used by the rest of the scene. So in short, this function is just a simple way to generate temporary textures entirely in memory without needing any external files. Now let's move on to the load image function, which handles the real portrait textures. This function takes in three things: the image URL, the target texture we want to update, and the vector that stores its size. Inside it, I start by creating a new image object and set its cross-origin property to anonymous. That just makes sure the image can load properly, even if it's being fetched from a different server or domain. Next, when the image finishes loading, the onload function runs. Inside it, the first thing I do is read the image's original width and height, and then update our texture size vector to store those dimensions. That information will later help the shader calculate the correct scaling and aspect ratio. I'm also logging out a quick message to the console, just so you can confirm that the image is loaded successfully along with its resolution. After that, I'm adding a safeguard for very large images. If the image's width and height exceeds the maximum supported texture size, in this case above 4000 pixels, we'll resize it proportionally to keep it within that limit. That prevents WebGL errors and ensures stable performance even with high resolution images. Once we have got the correct size, I create another temporary canvas, set it to the new dimensions, and draw the loaded image onto it using the 2D context. Then I convert that canvas into a new Three.js texture, the same way we did earlier, and again set both min and max filters to linear so everything stays smooth. Now, depending on which image we just loaded, I check whether the file name includes the word top or not. If it does, the texture gets assigned to the top image uniform in our display material, otherwise it's assigned to the bottom one. So essentially, this function loads the image, resizes it if needed, converts it into a texture that Three.js can use, and automatically plugs it into the correct shader uniform. And finally, in case something goes wrong, I have added an error handler. If the image fails to load for any reason, we'll get a clear message in the console telling us which file caused the problem, which can help you to debug the issue. At the end, the image source is set and the browser starts fetching it right away. Together, these two functions make the whole texture pipeline work smoothly. We use this placeholder texture right away, so we always have something visible on the screen. And once the real images finish loading, they automatically replace those placeholders without any visual glitch or delay. Next, we'll move on to the interaction handling and the animation loop. That's where we'll connect all of these together and bring the fluid simulation to life. First, I'm setting up the mouse move handler. Every time the mouse moves, we get its position relative to the entire screen, but we only want to track movement inside the canvas. So first, I get the canvas boundaries using getBoundingClientRect. Then I check if the mouse position is still within the canvas. If it is, I store the previous mouse position and then update the current one using normalized values, meaning we map the screen coordinates to values between 0 and 1. We also flip the y-axis by subtracting it from 1. This is because WebGL uses bottom-up coordinates, unlike the browser which starts from top left corner. Once that's updated, I mark the user as actively moving and record the current time, but if the mouse leaves the canvas, we right away set is moving flag to false. That way, the simulation fades out gracefully when you stop interacting. Next, I am doing the same thing for touch input. If there is at least one touch on the screen, I grab its position and prevent the default scrolling behavior. Just like before, I check whether the touch is inside the canvas area. If it is, I update the previous and current mouse vectors, same logic as with the cursor, and mark the user as actively moving. If the touch leaves the canvas or if it goes inactive for a while, we turn off the motion state. So between these two functions, mouse and touch, we are now tracking input across both desktop and mobile devices. After that, we have the window resize handler. If the user resizes the browser, I update the render size to match the new window dimensions, and I also update the resolution and device pixel ratio uniforms inside the display shader so that the visuals always stay crisp and scaled properly on different screen sizes and devices. And finally, we have the animation loop. This is the function that runs every frame over and over, and it's where the core of the simulation happens. First, we use request animation frame to call the same function again on the next frame. That's what keeps everything in motion. Then I check how long it's been since the last movement. If the cursor or touch hasn't moved for more than 50 milliseconds, we turn off the isMoving flag that triggers the fluid shader to gradually fade the trail away. Now comes the ping pong rendering. I grab the texture from the previous frame, swap to the next target, and alternate between them. This is what lets the simulation build over time and creates that persistent trail effect. Then I update all the shader uniforms for the fluid simulation. I pass in the previous trail texture, I update the current and previous mouse positions, and I toggle whether the user is currently moving. Once that's ready, I render the simulation scene into the active target, so we store the latest trail state off screen. Then I take that trail texture and pass it into the display shader. This is what actually gets shown on the canvas. And finally, I render the main scene back to the screen. This entire loop runs continuously, updating the mask based on user input and revealing the image underneath in real time, giving us that soft, fluid, brush-like effect that responds naturally to every movement. That's it, the full setup is complete. We have now got a working interactive fluid reveal using Three.js, custom shaders, and a clean full screen layout, powered entirely by mouse movement. Hope you found the video helpful. See you in the next one.